Of all the numbers that have fascinated humanity, from the simple perfection of whole numbers to the mystery of pi, one stands out for its turbulent history, the square root of 2. Its very discovery in ancient times shattered a fundamental belief, sparking a mathematical crisis that may have even led to murder. But beyond its infamous legacy lies a deeper intellectual puzzle. For thousands of years, we knew this number existed, but its true nature as an irrational number, a number that cannot be written as a simple fraction, wasn't firmly understood until the 19th century. In the ancient world, without this concept, mathematicians could only try to pinpoint its location on the number line through increasingly clever approximations. So, how did they do it? In this video, we'll explore one of the oldest and most elegant methods for calculating the square root of 2. Today, we understand the square root of 2 as an algebraic irrational number. Let's break that down. It's algebraic because it's a solution to a simple polynomial equation with integer coefficients. X squared minus 2 equals 0. The positive solution to this equation is, by definition, the square root of 2. Now, here's where it gets interesting. We know this number exists, but it has two mind-bending properties. Its decimal expansion never ends, and its digits never settle into a repeating pattern. This makes it irrational. But there's a crucial third property that often goes unnoticed. The square root of 2 is also computable. This means that even though we can't write down its infinite digits, there is a finite step-by-step recipe, an algorithm that a computer can follow to calculate its value to any desired precision. We can always get closer and closer with perfect accuracy, digit by digit. Heron's method is a powerful technique for calculating square roots built on a beautifully simple recursive procedure. Recursive means it uses the output from one step as the input for the next, creating a cycle of ever-improving approximations. To truly understand where this method comes from, let's start with a bit of geometry. Imagine a right-angled isosceles triangle where the two short sides are each of unit length, 1. The hypotenuse of this triangle is the length we're trying to find. Let's call it x. By the Pythagorean theorem, we know that x squared equals 1 squared plus 1 squared, which means x equals square root of 2. Now, let's think about area. The area of this triangle is simply 1/2. But there's another way to express this area. If we consider the hypotenuse, x, as the base of a larger configuration, we can find an alternative expression, which is x squared over 4. Imagine arranging 4 identical copies of our triangle to form a large square with their right angles meeting at the center. The outer sides of this arrangement create a square whose sides are each equal to the hypotenuse, x. The total area of this large square is therefore x squared. With the same logic, we can have a copy of this new square whose area can be given by 2 as well. Now, imagine placing these two squares side by side so that they share a common side, forming a rectangle. Recall that the area of each individual triangle can be expressed in two ways, as 1/2 or as x squared over 4. This means the first square, composed of 4 triangles, has a total area of x squared. The second square, also composed of 4 triangles, has a total area of 4 times 1/2 equals 2. Therefore, the total area of the newly formed rectangle is x squared plus 2. Now, observe the dimensions of this rectangle. Its width is 2x, the combined length of 2 square sides, and its height is x. We can also calculate the area by multiplying these dimensions, giving us 2x times x equals 2x squared. This gives us two expressions for the same area. 2x squared equals x squared plus 2. This leads us to a key question. If we have a rectangle with a known area of x squared plus 2 and a known width of 2x, what must its height be? The process of finding this height and the profound geometric insight behind it forms the very rationale of Heron's method. After introducing its rationale, now let's examine the recipe for computing the square root of 2, Heron's method, also known as the Babylonian method. First of all, this is a recursive algorithm. Think of it like this. We start with an initial guess, and then the output from one step is fed back in as the input for the next. With each cycle of this process, the result gets closer and closer to the true value, or in mathematical terms, it converges to the square root of 2. Here is the pseudocode that defines this method. For Heron's method to work properly, we need to set it up with a few key parameters. First, as you can see, the recipe itself is finite in length. It's just a handful of lines, each made up of a finite number of symbols. This satisfies the first crucial condition for computability. Next, our finite recipe must be guaranteed to stop. This is where the parameter n and the loop condition in line 4 come in. By setting n to a finite number of iterations, we ensure the algorithm will terminate, satisfying the second condition. Finally, the algorithm must produce an output that is arbitrarily close to the actual value. This precision is controlled by the variable x, which is repeatedly refined. The recipe is designed so that with each iteration, x homes in on the true value of the square root of 2. So with our conditions for computability met, let's bring this ancient algorithm to life and watch it converge. As discussed earlier, we initialize our parameters in accordance with the algorithm's requirements. An initial estimate or guess, say x of 0, the maximum number of iterations, and a counter to track how many iterations have been carried out. This counter guarantees the algorithm will stop. For the initial estimate, 1 seems to be a plausible value, since the square root of 2 is the hypotenuse of a right triangle whose short side is 1. But it is important to note that, as we will show subsequently, Heron's method is extremely powerful, so that no matter what value you initialize with, it is destined to home in on the square root of 2. Therefore, for the time being, any initial value is fine. In conjunction with this powerful convergence behavior, we will set the maximum number of iterations to just 3. Then we start the algorithm. In the first iteration, a new value of x is determined in line #2 with the algebraic operation we devised before. Since our initial estimate is 1, our new estimate is updated to 1.5. In the next step, we increment our counter to track the iteration count, and we then check whether we have reached the maximum number of iterations allowed. Determining that the condition is not satisfied, we are routed back to the next iteration. If you remember from the previous iteration, our current estimate is now 1.5. Hence, our new estimate becomes 1.416 to 3 significant digits. If we carry on with the steps based on the recipe, after the third and final iteration, our algorithm returns 1.414 to 3 significant digits and stops.
Why is Heron's method so powerful that it converges to the square root of 2 no matter what initial value you start with? The answer provides fascinating insights into mathematics and touches on important concepts like stability, attractors, and fixed point theorems. While we won't dive deep into the formal details of these concepts today, we will hopefully establish an intuitive link to them. To understand this, let's examine the underlying nature of Heron's method. Here on the screen, we can see a graph showing how the method evolves for all possible starting values. As you can see, when the value on the horizontal axis, which is the input to the method, matches the value on the vertical axis, which is the output that becomes the next input, the method has reached its goal. This intersection point is the true value of the square root of 2. Beyond this exact point, It's crucial to note that in the vicinity of the square root of 2, the algorithm also provides an extremely close approximation. This is why the square root of 2 is known as a fixed-point attractor for Heron's method. This concept guarantees that the further we iterate, the closer we get to the exact value, effectively being pulled in towards the solution. For those interested in how this attractor behavior manifests in Heron's method for the square root of 2, we can investigate the inner workings of each iteration. First and foremost, Heron's method is a recursive, iterative algorithm. This means we apply the same rule or mathematical function repeatedly, using the output of one step as the input for the next. From a pure mathematical perspective, this is known as a fixed-point iteration. Even though there's only a single rule, each iteration effectively creates a new function by chaining the original rule with itself. The sequence of values generated by this process, our successive estimates, is known as a Picard sequence. It is this iterative chaining that leads to the powerful behavior we observe. As the iteration count increases, the fixed-point attractor guarantees that our estimates are pulled closer and closer to the true value. After just a few iterations, this process yields the square root of 2 to a remarkably high number of significant digits. In Heron's method, as we can see here, each iteration produces a new improper rational function. Interestingly, the numerator of this function is always of an even degree, while the denominator is of an odd degree. As the iterations progress, the sequence of values generated by these functions converges to the actual value of the square root of 2. What's truly remarkable is how the composition operation itself acts as a forcing mechanism. No matter what initial value you start with, this iterative process inevitably pushes it closer and closer to the true value.
Before we conclude, let's investigate the reason for such fast convergence. Recall that the goal of a fixed-point iteration is to find a value that remains unchanged through repeated application of the function, the fixed point. This rapid convergence hints at a fascinating underlying mechanism. The iterative process effectively constructs, through its chain of compositions, an approximation of the inverse of the original function's behavior around the solution. Think of it this way. Each iteration switches the roles of the function's domain and range. This creates a powerful trap-like behavior in the vicinity of the true value. Once an estimate enters this region, the iterative process forces it to home in on the square root of 2 with remarkable efficiency.
And so, from a geometric puzzle that challenged the ancients to a recursive algorithm that powers modern computation, Heron's method gives us the square root of 2. It's a journey from a simple triangle to a profound mathematical idea that even the most infinite and unruly numbers can be tamed by a finite, step-by-step process. Heron's method doesn't just calculate, it demonstrates a fundamental truth that within the chaos of irrationality there exists a powerful, predictable order waiting to be uncovered one iteration at a time.